Hello grade 10. So Mrs. DeRoda and I just got together and we thought we'd do an introductory practical for you, online teaching style. So we are just doing some stoichiometry in the background there. We're doing some calculations and we're going to work some stuff out to show you some reactions and then introduce you to the calculations that we are going to do with the next section of chemistry that's coming up. Starting you with stoichiometric formula today. Stoichiometry is the relationship between relative quantities of substances taking part in a reaction forming a compound. So you already know that all chemical equations need to be balanced to ensure that you have the same number of atoms present and that the conservation of matter is upheld. Let's now look at an example of an equation and show you why balancing an equation is important. So here we have an example of an incomplete chemical equation, and I'll show you why you need to first of all have the formula in your chemical equation correct, and then why your equation needs to be balanced, and how that equation then gives you a ratio with which to work. So the one reaction we are going to deal with today, we are going to burn magnesium ribbon in the atmosphere, which will then burn oxygen, and we are going to produce magnesium oxide. However, we know that oxygen exists in nature and that it is diatomic. So that immediately gives you two atoms that you're working with, which will affect your calculations. So very important to get that right. And then we need to balance the equation. Here we only have one atom of oxygen on the left side of the equation. We've got two atoms of oxygen on the left side of the equation, only one on the right. So we need to balance that out. That gives us the two atoms of oxygen that we need, but now we are short one magnesium, so we balance it like that, and we have a correctly balanced equation. So two atoms of magnesium react with one diatomic molecule of oxygen to produce two molecules of the compound magnesium oxide. Now what that does in terms of giving us a ratio is today we are going to look at the ratio of magnesium to magnesium oxide, for example, and that tells us that these two substances react in a 2:2 ratio. So that's magnesium to magnesium oxide. But for example, and then with calculations, we know that when we're converting numbers that the ratio it's going to be 1:1, obviously, because we simplify. However, if we are looking at, for example, if we were looking at oxygen to magnesium oxide, we would know, so oxygen to magnesium oxide, that is a 1:2 ratio. And when you are doing your calculations, you need to be aware of those ratios so that you can work with the values that we are speaking about. First, I need to explain to you some of the formula that we are going to use in our calculations. So, you will see later in the video that Mrs. DeRoda will use all of these equations to do some calculations and demonstrate for you that we can predict the mass and the volume of products that are formed depending on whether gases or solids are formed. So, this formula here you will use very often. This little n, okay, so the little letter n is the number of moles. Now, we understand that you don't yet know what a mole is. We will teach that to you in your first lesson. It refers to Avogadro's number. It's a number of atoms. So just like we talk about a dozen eggs as being a number, and we know that when we talk about the number a dozen, we know there are 12 of whatever we're talking about. When we talk about a mole, we're talking about a fixed number. It's a very large number. It's 6.022 times 10 to the power of 23. But it's just like a dozen. So that's what a mole is. We will go into more detail with you when we teach you live for the first time. So that's what the little letter n stands for. The little m is the given mass of whatever you are working with. So today we were working with magnesium and zinc as a given mass. That's what we knew the mass when we started, so that we could do that calculation. And then this capital M is molar mass. So that is the mass of 1 mole of that element or compound, and you can calculate that using the relative atomic mass of the periodic table. However, if your periodic table only gives atomic mass, then you just use atomic mass. Okay? So if you have a look on your periodic table, you will see that the atomic mass of magnesium is in the region of 24. I think 24.3 something is the relative atomic mass, and for lead it is approximately 65. So that's where we're getting that value from. It's that is the mass of that same number. So you can think of it as like 1 dozen, although it's a crazy high number, but that is how much that amount or that number of atoms weighs in grams, and you pull that off the periodic table. Okay? Then when we're using gases, like we were producing hydrogen gas in the one demonstration that we did for you, we have another calculation that gives us the number of moles, and there we can calculate using the given volume of a substance when it is a gas, and we put that over the volume that 1 mole of gas will always occupy at standard temperature and pressure. So STP is standard temperature and pressure, which is 1 atmosphere of pressure at 25 degrees centigrade is the standard temperature and pressure. So 1 mole of any gas at standard temperature and pressure will always occupy 22.4 cubic decimeters. And you will see that we use that information to do the calculations today. And obviously that is also where we get the mass, the molar mass of any substance from. It all relates to these calculations, and all of these equations are present on your data sheet, and you will have to learn how to manipulate them and change the subject of the formula in order to predict results depending on what you're asked. Now we move on to showing you the reaction where we put zinc metal going into the test tube and reacted it with a very concentrated hydrochloric acid that Mr. Girodo is now pouring in at the top. We then opened the tap, let the acid into the test tube and sealed it off. You'll see we're using a side-on test tube, and then displacing the gas through the rubber tube into the water bath, and then displacing the water downwards. We've just used colored water. That is just colored water that we've put in an upside down burette, and the zinc metal that we used. And we used a mass meter that we zeroed and then added 0.2 grams of zinc. So there goes the 0.2 grams of zinc into the test tube, rubber stopper closed, draining in the hydrochloric acid. We're not worried about the volume of acid, and we seal it off. So now we have created a sealed system. You can see the rubber stopper and the side-arm test tube leading into the water bath, where we are then collecting the gas, and then the gas immediately traveling up and displacing the water downwards. So we're collecting via the downward displacement of water. The hydrochloric acid that we used was very concentrated. You could smell it. It was very strong, so that is why the reaction was so quick. Now obviously we've got zinc, which is a metal, and we are using hydrochloric acid, so that is a metal plus acid reaction, and we know that your product will be a salt, which is zinc chloride, which will be left behind in the test tube, and the gas produced will be hydrogen gas. There's a look at the increments on the side of the burette with a good old periodic table behind it so that we can see the values. You can see the reaction happening in the test tube. This went on for some time and continuing to displace the water downwards. Again, the water is just colored water. It's just water with colorant in it so that we can see it clearly. And here you can see the setup of the rubber tube going into the bath and collecting the gas so that the gas displaces the water downwards.
It's almost done.
So, Mrs. Girodo, when you put your hand on that test tube there, what does it feel like?
It feels hot.
What does that mean?
It's exothermic.
So, a reaction that spontaneously produces heat is an exothermic reaction, guys. Okay. So, that test tube is warm. Now we are inverting the burette so that we can check the volume of gas that has displaced the water. We have a 50 cubic centimeter burette, and we have displaced 16 cubic centimeters there. Subtract the 50 and it gives us 34 cubic centimeters. Now let's do a calculation to check if we were right. Yeah.
Okay, from the experiment where zinc reacted with hydrochloric acid, we want to find the volume of hydrogen gas. So if we start with a given mass of 0.2 grams of zinc, we have to find the number of moles because we're going to use a molar ratio. So your equation is balanced. So if it's a 1:1 molar ratio, so if this one's mole is mass over molar mass, so 0.2 divided by 65 off your periodic table, and that gives us...
Which is the molar mass of zinc.
Molar mass of just zinc. So it ends up being 0.003 mole. So if we use the molar ratio here of 1:1 zinc as to hydrogen gas, then the number of moles would be 0.003 moles for hydrogen as well. Okay, so that's for hydrogen. So if we want the volume, mole is volume over standard volume. So we're going to assume it's an STP. So if I manipulate mole multiplied by standard volume. So the same number of moles, 0.03, multiplied by standard volume that will be on your data sheet. And that gave us
0.034 cubic decimeters.
4 decimeters cubed. But our burette calculated it in centimeters cubed, so 0.034 decimeters cubed would have read as 34 centimeters cubed, and that's what you saw in the burette after to perfection, because the burette is 50 cm3 minus the 16 gave us the exact 34 centimeters cubed of hydrogen gas produced.
Which doesn't often happen in chemistry. So we will, at the end of the section, we will talk about percentage yield. And we got 100% percentage yield for the reaction, which was quite surprising. But there you go. So because we know that 1 mole of zinc will produce 1 mole of diatomic hydrogen, that's the ratio that we're talking about there with the 1:1. And we can predict the volume of hydrogen gas that is produced. And we managed to reproduce that in the reaction to perfection. And here is the value that the calculator gave, but that's in cubic decimeters. And just a review of the whole calculation. Now, just to show you that if we change the amount of reactant, that we will vastly change the amount of products that are formed, we did the reaction a second time with 0.49 grams of zinc. And we repeated the calculation and calculated that we should get 167 cubic centimeters of gas produced. So now let's have a look. Exactly the same experiment setup, except that we are using more zinc at the start of the reaction. Look how quickly it produces gas, and you will see that the volume of gas is much greater. Remember, our burette is only 50 cubic centimeters, and very quickly we push all the water out of the bottom of the burette, and we start bubbling hydrogen gas up out of the water bath. Now we're just going to demonstrate something about the conservation of matter. We are now using magnesium, 0.13 grams of magnesium according to the mass meter, and we are burning it in the atmosphere, which contains oxygen. Now, from your grade 9 practicals, you should know that that gives you a very bright white flame, which you can see there, and you can also see the gas particles moving around, exhibiting Brownian motion, by the way. But there it's an oxidation reaction forming magnesium oxide. So we are forming a metal oxide. Just needs a little bit more flame to complete the reaction. The magnesium that we started with was not absolutely clean. It would have been partially oxidized, so in this reaction we cannot predict how much magnesium we are forming because we don't know how much magnesium is pure magnesium and how much that we started with is already magnesium oxide. However, we can completely oxidize the magnesium in the crucible, and we can show that we have gained mass through the reaction. Now, the oxygen that we are using as our second reactant is obviously the oxygen that is present in the atmosphere, and now Mr. Girota just mistakenly zeroing the mass meter there, but we calculated the mass of the crucible with the magnesium oxide and then subtracted and got a value of magnesium oxide. Okay, so now we've got our second reaction where we reacted magnesium in the atmosphere which contained oxygen.
Okay, now in the equation of magnesium that reacts with oxygen, all we're going to look at here is how the calculations can assist us to see how much oxygen has reacted. So in the beginning we had magnesium 0.13, the crucible weighs that, so together the two of them weigh this. After burning it and gaining oxygen to form magnesium oxide, it weighed 53.28. So if you look at the difference between the two, 53.28 subtract 53.27, we have actually gained 0.01 gram of oxygen gas. So you can use this to help you with the law of conservation of mass, because the two reactant masses have to add to the product mass. If it is in a closed system, and we're lucky enough with our system that we got a gain of mass of 0.1 grams.
Now this reaction is what did not take place in a closed system, and also the magnesium that we used would have already been partially oxidized, so it would not have been pure magnesium, so we can't demonstrate a predictable outcome with this one, but we can show that there has been an increase in mass, and that is the oxygen forming part of the compound and then contributing to the mass of the final product in the magnesium oxide. This video was made at the Durban High School during the COVID-19 lockdown for grade 10s following the CAP syllabus in South Africa. Thank you to Mr. Charles Moodley and my colleague Michelle Girota for making the video together. If you enjoyed the video and would like to use it in other parts of the country or other parts of the world for that matter, you are most welcome to do so. We hope you enjoyed it.